Alright, starting another video here. In this video I wanted to talk about a problem that I ran into at work. We had to supply power to the what's called the EUT, which is the equipment under test. The problem is that we only knew how much current draw the equipment under test needed to be supplied. The amount that it needed was 3 amps. So what we could do is we could add power cables. You have on the power supply over here on our outputs, we got a high side and a return side. This is a DC power supply, by the way, so it's supplying DC power. And then, first thing maybe we could do is just turn on the power supply, turn it up until the current read 3 amps on the power supply. The problem with that, however, is that our power supplies are not calibrated. So what that means is that whatever value the power supply displays is not necessarily what is actually being supplied to the equipment under test. So the first problem we run into is how do we verify that we have the 3 amps going into the equipment under test. So that brings in our next piece of equipment. In this case, it's the digital multimeter. One thing that we can do, let's see. So the thing about multimeters is you can take what we can do to measure the current going into the EUT is we could tap off this high side line and go into one of the current ports on the multimeter and then come out the common port and then bring that the rest of the way, and this high side line is broken. And what the digital multimeter will do it'll read the current going through. This is one possible solution. However, it requires damaging the power cables, or at least breaking the circuit. Another issue that you could run into is there's an internal resistance on the multimeter that the current will be going through, and you're basically creating what's called a voltage divider. You have a little bit of voltage drop internally on the resistor, and then you have another voltage drop on the equipment under test. So if you're stealing some voltage across the digital multimeter, then maybe the EUT isn't getting the proper voltage that it requires. So that was another dead end. So that leads to the next puzzle piece, which in this instance is a resistor. So what this resistor is going to do is it's going to act in place of the multimeter's internal resistor, and we're actually going to not break the system, but let's see, let me reorganize this. Hold on one second. Alright, so in this instance we've just added a second wire. We've gone from the high side of the power supply into one end of the resistor. So this is a big resistor, and then added another cable from the output of the resistor out to the equipment under test. So now what we have is we'll have to measure the voltage drop across that resistor using the multimeter. So in this case, when we have 3 amps going through, and I also have to size the resistor value to a level that I know that won't be too dangerous. So basically, if all I'm given is there's going to be 3 amps into the equipment under test, we're not expecting a high voltage, maybe somewhere around 24 volts or 25. So if we have 3 amps going through, if we had just a 1 ohm resistor, then Ohm's law tells us that the voltage drop across the resistor should be 3 volts. And if there's 3 volts and 1 ohm, then the power requirement is V squared over R, which is just 9 over 1 watts. So I had to find a resistor that would be able to support those power requirements of 9 watts, and I just used roughly 1 ohm to make the conversion from current to voltage pretty easy to do. So that takes care of measuring the output current of the power supply, which tells us how much current the EUT is drawing. Since we can't trust the the displayed measurement on the power supply, another thing we can do is just use a calibrated multimeter and measure the voltage drop across directly, and that would totally be fine to do. However, what the customer's request was to be continuously monitoring the voltage, power supply voltage, and the current into the EUT. So a multimeter won't work in this instance because it doesn't have a recording function. Alright, so since that's the case, since I can't use a multimeter, we're going to bring in the laptop and the DAC. Now, a DAC is a digital data acquisition device. So it basically will, and it'll log it. So basically, it'll work as a digital multimeter. Just have to run it with some software on the laptop. However, the things we have to take into consideration with the DAC is its voltage limits. So it definitely can't take more than 10 volts. I tried to keep it around 5. So the problem with using the DAC, or one of the challenges with using the DAC, was that we knew the power supply needed to be around 24 volts, but to be able to monitor that voltage safely with the DAC, we needed to create a voltage divider. So let's talk a little bit about how a voltage divider would be able to help us in this situation. So I'm going to switch to drawing out a circuit to make it look a little bit more understandable. We have our power supply with some voltage, and then what we're going to do is create a voltage divider, and we're going to have some resistor value here and some resistor value here. And what we're going to do is we're going to you hook the DAC up to the second resistor and measure the voltage across that resistor. So the first thing that we can do when looking at this circuit is we can kind of group these two resistors together and then just look at what's going on with both of them together. You have the voltage source, and then you have some box circuit, and what we know from circuit analysis will tell us that the voltage across the I'll just say L for load, the voltage across the load is the same as the voltage source in this case, because we have one end of the load connected to the positive side of the battery or power supply, and we have the negative side tied to ground. So whatever voltage we measure across the source is the same as we'll measure across the load there. Okay, so I'm gonna say VI for V in and VO for V out. Well, yeah, I'll just keep it a VL for now. And so what can we determine from just looking at this simpler circuit? We should be able to figure out what the current through the circuit is this way. Alright, so yeah, what can we say about this circuit? Just looking at it. Well, we know there's a certain amount of current going through this circuit. Now, what is that current equal to? Well, using Ohm's law, V equals I times R, or rewriting this, we have V over R equals I. So in this case, the voltage is VI, and the resistance is the summation of the two resistors, R1. Remember, inside here is R1 and R2. So and they're in series, so they're just additive. So yeah, that's why I'm confused. I have a VI and an I. Okay, so that equals I. So that equals the current that goes through the entire circuit. So taking that information back to our initial drawing, we have VI and the DAC is VO. So remember, we have the current that's going through here is equal to VI over R1 plus R2. So now that we know the current that's going through, we want to know what the voltage drop across the DAC will be. So again, using Ohm's law, V equals I times R, and it's VO in this instance. So because VO is what we're looking for, VO equals VI divided by R1 plus R2. Remember, that's just the current component. That's what we found to be the current going through the system. So we know that is the current, and then the resistor is And then the resistance value is just this resistor. Remember, we're not trying to see anymore what the voltage drop across the whole system is. We just want to see what the voltage drop across R2 is. So we multiply by the resistor value R2. Okay, so now let me just rewrite that a little bit to clean it up. We see that VO is equal to V in times R2 over R1 plus R2. So that's a general equation, a general formula for a power supply with a resistor, with two resistors in series. And if you are just measuring, so you have V in and you have VO. So if you want to determine the value of VO, you take the voltage input and then you multiply it by a ratio of the resistor that you're interested in divided by the resistors in series. So that's the equation we're gonna start looking for. Okay, just to take one more look at the circuit that we have and draw it out one more time. We have our power supply, voltage in, and we have some R1 and some R2, and that's the voltage out. Alright, so at this point I started plugging in my assumed values. We knew that we needed roughly 24 volts as an input source. The VO, which is the DAC, has to read less than 10, so I clamped it at 5 volts. So assuming we see 5 volts across the DAC, we'll know that there's 24 volts across the input source, and we'll know that by choosing specific resistor values, and those resistor values can be determined from that equation that I wrote up earlier. Mainly VO equals V in times R2 over R1 plus R2. So in this instance, my VO needs to be 5 volts, and my V in, I'll just leave as V in because it's going to be somewhere around 24 volts. Whatever is required to supply the current requirement is going to be what the voltage is. So so R2, well, let's say in the instance we do have 24 volts. What are the R2 and R1 values to make this a true statement? Well, if we want to, let's make it a little bit easier. What if we had 5, and I'll drop the units of volts, but we had 5 times some number x. 5 times some number x is going to get us to be 24. So to solve for that, we just divide 24 by 5. So we get 24 divided by 5 is equal to 4.8. So we know that 5 times 4.8 is equal to 24. 24 divided by 4.8 is equal to 5. So what that tells us is that we're going to have 5 volts times this. Now I'm switching this all the way over to the other side, so I do R1 plus R2, and R2 is equal to 24 volts. So this and this equation are analogous to each other. We have the 5, we have the 24, so all we need to do is figure out what x is. What x is. We did find out what x is, so we need to find out what this group is. So we're going to set this equal to this, and we're going to find a solution. Alright, so yeah, let's set them equal to each other. We have R1 plus R2 over R2 is equal to 4.8. Alright, so if I multiply both sides by R2, we get R1 plus R2 is equal to 4.8 R2. Now I want to move R2, the first R2 to the other side, so I get R1 is equal to 4.8 R2 minus R2, and that means that R1 is equal to 3.8 R2. So there's a ratio. Whatever I choose to be R2, R1 has to be 3.8 times that value. So let's see. So there's some degrees of freedom here. In this instance, I chose R2 to be 5 ohms, just because that's a nice round number. That's the resistor that we had laying around. And R1, that means has to be 19 ohms, which we also had laying around. So again, we need to look at the power requirements of each of the resistors. If we have 5 volts going across the load resistor, then the power is equal to V squared over R, which is 25 over 5, which equals 5 watts. So I need at least 5 watts for this resistor. And then what is the remainder of the voltage drop across R1? So to determine that, we take the total voltage, which the assumed voltage is going to be 24, and we subtract the 5 volts that's going to be dropped across R2. That means that R1 will have the other 19 volts dropped across it. So the power requirement for this is going to be 19 squared divided by 19, which is just 19 watts. So for R1, we need a resistor that's at least 19 watts, and all of our resistors are way more than that. So that was fine. Alright, so here is the final setup that I used to monitor the voltage and the current into the equipment under test. The high side, if we trace the high side from the power supply, we see it goes into the high side of the current resistor, which goes directly into the equipment under test. That way we can measure what the current is into the equipment directly there. Also tapping off the high side, we go into our voltage divider network. So first we have some sort of voltage drop across the first resistor, and the voltage drop across the second resistor will be much smaller now that we've lost some of that voltage. So that should be a low enough number for the DAC to measure safely, and we have a conversion to back calculate what the power supply voltage actually is. So yeah, that was a fun little project at work that I had to use some of my old circuit analysis techniques on, and worked out pretty good.